So we've seen several differential equations now where we found a complete list of solutions. Well, we found some solutions, and we've asserted that those solutions that we found were independent. Now let's consider, how do we know that? How do we know they actually are independent? So here's an argument that will work in the situations that we've considered. So in particular, these are going to be cases of all real roots, not necessarily distinct real roots, possibly repeated real roots. So for example, here, these are the solutions that we would get if the characteristic polynomial had a root of -1 with a multiplicity of 1, a root of 2 with a multiplicity of 2. Notice e to the 2x. First it's 1 times that, then it's x times that. And then another root of 3 with a multiplicity of 3. And again, the 3 solutions that our previous theorem tells us are solutions. Okay, so with all of these solutions together, how do we know that this list is independent? Okay, well, the question is determined by looking at linear combinations that add up to 0 and asking, can I conclude that these coefficients must all be 0 in order for this to work? Is it true that the only way to make this happen is if all 6 of these numbers are all 0? Okay, so I'm going to assume that this equation is true. My goal will be to show that all of the coefficients, C1 through C6, are 0. So here's the clever move. By the way, this is a different method than is done in the book. I like this for certain reasons. We're going to take this equation, we're going to multiply through by e to the -3x, and then take a limit as x goes to infinity. And we'll see why after we do this. Okay, so multiplying through by e to the -3x, the coefficients all change significantly. Right? In particular, these become decaying exponentials, and these, well, you probably saw this coming. The e to the -3x cancels the e to the 3x that's there, and you get just polynomial that's left over. So multiplying through by e to the -3x gives us this, and then saying limit as x approaches 0 gives us that. And of course, doing the same with the right hand side gets you 0. Still 0. Okay. All right. Well, good news. These are decaying exponentials. Their limit as x approaches infinity is clearly 0. I don't even care what those constants are, C1, C2, C3. In all cases, that limit is equal to 0. And that means we're interested only then in this and the fact that its limit is equal to 0. This is actually something we can understand very well, because this function inside of here, this function whose limit is equal to 0 is a polynomial. In fact, it's a quadratic polynomial. And there's only one way that a quadratic polynomial can possibly have a limit equaling 0 as x approaches infinity. The only way that could possibly be is if all 3 of these coefficients here are 0. So therefore, we have shown that that's got to be 0, and that that's got to be 0, and that's got to be 0. So we're halfway there. Our goal was to show that all the coefficients were 0. We see that these 3 of the 6 are already. Okay, so that being the case, with these terms gone, our equation here becomes this, and we repeat. Same basic idea. Now, again, the idea here was that there's something about these terms. I guess I didn't say this yet. The idea was that there was something about these terms that was peculiar, unique, and that what that is that all 3 of these terms have the biggest factor, the biggest exponential factor anywhere in the equation, e to the 3x. That's the highest exponential in this equation. That's only e to the 2x. That's only e to the 2x. That's e to the -x. That's not even close. Okay. So therefore, these 3 terms are doing something that these terms couldn't possibly match. These terms are simply growing faster than these possibly could. And so this move here, this move of dividing by e to the 3x and taking a limit as x approaches infinity, is simply a way of getting these out of the way so that I can isolate those terms in particular. And conveniently, an easy conclusion can be drawn at that point. So that's the idea. So how do we apply that same idea now here to this equation? Well, the highest exponential here is e to the 2x. So with that in mind, I'm going to multiply by e to the negative 2x, take a limit as x approaches infinity. This becomes this. This limit here is obviously 0, so I can throw that term away. And therefore, I have that. And this is another polynomial. Here we have another polynomial that as x approaches infinity, approaches 0. There's only one way that could be possible, and that's if both of these coefficients themselves were 0. So that means that these coefficients go away. And these two terms, therefore, are gone. And we're left only with that. And at this point, there's no need for any fancy moves. At this point, it's pretty clear that this equation tells us that C1 is equal to 0 as well. So grand total, I have shown that C1, C2, C3, C4, C5, and C6 are all equal to 0. That's what we were trying to show. Therefore, the list of functions is independent. Okay, so this is a clever idea, clever move. Something along these lines will always work for, when you have exclusively real roots. And what I have on the next page is just a statement that this generalizes. Here's the statement. This is a theorem. You students may use this. You may cite this theorem in this course. And here is the theorem. Constant coefficient linear differential equation, homogeneous, characteristic polynomial. If it has all real roots, our previous theorems, of course, giving solutions of this form, these solutions are independent. So, said differently, the solutions that you will write down for these differential equations whose characteristic polynomials have exclusively real roots, those solutions that you will write down from our existing theorems will always be independent. And the proof that I have written down here is just, it's the same idea that we have on the previous page. Multiplying by the appropriate exponential, taking a limit as x goes to infinity, making an observation about how polynomials approach 0, and repeat. So same idea as on the previous page.